Hello everyone! In this video we will work through the formulas from our previous lecture. So let's take a simple example and work through the steps of the definitional formula. Suppose you have a population with 4 numbers, 1, 3, 5, and 7. Step 1 is to find the mean. So 1 plus 3 plus 5 plus 7 is equal to 16 divided by 4, which gives us a population mean equal to 4. Step 2 is to find the deviation score. We subtract the mean from each number, from each x value. So 1 minus 4 is equal to negative 3, 3 minus 4 is equal to negative 1, 5 minus 4 is equal to 1, 7 minus 4 is equal to 3. Now to double check your math in this step, the sum of the deviations always equals 0. So we did this correctly. Step 3 square each deviation. So we're going to take negative 3 squared is equal to 9, negative 1 squared is equal to 1, 1 squared is equal to 1, and 3 squared is equal to 9. Step 4 we add up the results. 9 plus 1 plus 1 plus 9 is equal to 20. This is our sum of squared deviations, or SS. Step 5. Divide the sum of squares by n, or nu. So we take 20 divided by 4 is equal to 5. This is our population variance sigma squared. And finally, step 6, we take the square root of 5, and that equals 2.2361. This is our population standard deviation, sigma. The interpretation for this population parameter, sigma, from our data set of 1, 3, 5, and 7, is that the average distance of the scores from the mean is 2.2 points. Notice how many calculations are needed here and how many ways to make calculation errors. Now let's take this same example and work through the steps of the computational formula. Step 1, square each score and add the squared score. So 1 squared is equal to 1, 3 squared is equal to 9, 5 squared is equal to 25, and 7 squared is equal to 49. Add up the results. 1 plus 9 plus 25 plus 49. The sum of x squared is equal to 84. Step 2, add up the scores, square the sum, and divide it by the number of scores. So 1 plus 3 plus 5 plus 7. Sigma x is equal to 16. Square the sum, 16 squared is equal to 256. Divide the result by the number of scores. sigma x squared divided by 9 is equal to 256 divided by 4, which is equal to 64. Step 3. Subtract your answer in the second step from your answer in the first step. 84 minus, whoops, this should be 64. So 84 minus 64 is equal to 20. As you can see, we get the same sum of squares, SS, with less calculations and less ways to make calculation errors. Just don't make the same error I just did. So the next two steps are the same as the definitional formula, where population variance is 5, population variance is equal to 5, and population standard deviation is equal to 2.2. Right? One of the goals of inferential statistics is to draw conclusions about the population based on limited information from a sample. Samples are different from populations. Samples have less variability, and calculating sample variance and sample standard deviation in the same way that we do for a population would result in a biased estimate of the population parameters. We want our sample statistics to be unbiased estimates for the population parameters. In order to remove this bias, we will need to divide our sum of squares by n minus 1 instead of n or nu. For sample variance and sample standard deviation, the sum of squares is calculated in the same way as before. So the numerator stays the same. Our denominator is the only thing that changes here. The denominator changes from nu, number of scores, to n minus 1. So using our previous example, we're looking at the same data of 1, 3, 5, and 7. Remember that our sum of squares, SS, was equal to 20. This doesn't change because the numerator of our formulas do not change from population to sample. What changes is the denominator. So now, to calculate sample variance, we need to divide sum of squares by n minus 1. So 20 divided by 4 minus 1 is equal to 20 divided by 3, which is equal to 6.667. This is our sample variance, S squared. To calculate sample standard deviation, we take the square root of 6.667, and that gives us 2.58. This is our sample standard deviation, S, 2.58. The interpretation for this sample statistic, S, from our data set of 1, 3, 5, and 7, is that the average distance of the scores from the mean is 2.6 points. Standard deviation can be difficult to interpret as a single number on its own. Basically, a small standard deviation means that the values in the data set are close to the middle of the data set on average, while a large standard deviation means that the values in the data set are further away from the middle on average. Why does this matter? Another goal of inferential statistics is to detect meaningful and significant patterns in our data. Variability in the data influences how easy it is to see these patterns. High variability hides the patterns that we would be able to see in low variability samples. So we want small standard deviations in our sample data. Small standard deviations represent low variability. Think of low variability and small standard deviations as scores that are closely clustered around their mean, which will make it easier for us to find meaningful patterns in our data. So we've just completed Module 1. Again, lots of information to take in. Remember to practice the calculations and think about the logic of each formula. This will help you remember which formula to use when. Make sure to complete the Cengage MindTap homework for chapters 1, 2, 3, and 4. I've also assigned lab number 2. It's a sample quiz to help you practice the concepts you've learned and has similar questions to the proctored exam for chapters 1, 2, 3, and 4. Let me know if you have any questions. You can always send me a message through Canvas inbox.